Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In the previous two videos, we saw something reassuring. Measuring error in y makes the regression noisier but doesn't systematically bias the slope. Unfortunately, the story changes completely when measurement error occurs in the independent variable. And this is the case econometricians really worry about, and the intuition for why it's different is also very visual. Suppose that the true relationship is as follows. So we've got true relationship, y being equal to beta 0 plus beta 1, x star plus an error term. Okay, so the x star is the true explanatory variable. And unfortunately, we don't observe this x star directly. Instead, we observe an x which is equal to x star plus some v. Okay, v here is the classical measurement error. It's a random mean zero uncorrelated with the x star in v. So I'm just gonna write this in here. So the covariance between my x star and u is 0, and the covariance between, and not u, but v, and also the covariance between u and v, that's also 0, okay? So the regressor itself is measured with error. Everything else, the y, the u, is exactly as it should be, so only x is the one that is contaminated. Now, if we compare these to the y error case, we had that the y is equal to y star plus v, and x was clean. So here it's the opposite. Y is clean, but x is contaminated. So same structure, but symmetric. And that's what brings about those different consequences. Let's look at a concrete example to put a little bit perspective to these kind of measurement error. Let's say that we want to estimate the effect of education on income. So again, we've got income as a function of education, and we want, just like in the measurement error with the x, to see these results. Now, education is the one that has a problem, so it's collected from a survey and people report their own years of schooling. So let's say you could have someone with 15 years of education, he reports 14. Someone with 12 years of education reports 13, and then someone with 10 years of education, let's say, reports 10. So it's correct by chance. Education itself is now measured imperfectly. The variable we're using to explain income contains noise, and this is extremely also common in practice because years of education, hours work, consumption, expenditure are all typically self-reported and therefore subject to this measurement error index. So now what is different? So what does OLS try to do? It tries to explain changes in y using the changes in x, but now x is wrong, okay? We've introduced noise into the very variable we're using to explain the outcome. OLS doesn't know x is measured incorrectly. It treats the observed x as if it were the truth, and that's why the mistake has consequences. So this is the fundamental problem. The OLS is trying to measure how y responds to x, but the x isn't observed, like it's not real what we're observing. It's a noisy version, and noise in your explanatory variable is much more damaging than noise in your outcome. If we were to draw this visually so that you can see, and I'm gonna take a slightly different approach for this one because with the y, it was quite obvious, okay? Why the actual slope remained the same. So what happens in here? Let's assume this is my real data, okay? And let's assume this would have been my fitted line, okay? What I'm going to do is take this with me and paste it here as well. Then because the measurement error is in the X, so it means you are going to go left and right because it's no longer with the Y variable, it's in the X variable. And any changes in the X variable, it means like you're going either to the left or to the right, okay? So it means that now this is how they are moving. This is how they are moving, okay? So the new version basically of these points is no longer what you had in here, but it could be something like this. Okay? And as you can see, it's more dispersed, but more than anything, it doesn't seem like now this line is the one that is the best. It does seem like, well, maybe it could actually be slightly more flatter. Okay? So now this looks like it's better. Okay? You have the cloud, which is stretching sideways. So the relationship becomes more diffuse. Okay? So if observations move left and right randomly, what happens is that the cloud becomes wider, more diffuse along the x-axis. The data points that should be far from the mean of x get pulled back toward to it. So this relationship now looks weaker than what it really is. So as you can see, I drew this new regression line visibly more flatter than the true line, okay? So the regression line begins to flatten. The estimated slope is smaller than the true slope, okay? Now, don't worry about the formula yet. That will come in a different video. So for now, just hold on into this picture. We've got the clear contrast from what happened when you had the measurement error in the Y variable. So here you've got horizontal noise that flattens the line. Okay. For instance, if we were to make a ruler analogy, imagine estimating the relationship between height and weight. Okay. Every ruler has random errors. Some heights are measured too short, some too tall. The true relationship between height and weight has not changed overall because biology is the same. But now the data show a weaker relationship because noisy height measurements blur the true pattern. Say the relationship overall will have been weakened, and not because taller people have stopped being heavier, but it's just because our measurements became less accurate. And crucially, this isn't fixed by getting more observations. More data with the same noisy ruler gives you more noisy observations. So the bias persists regardless of sample size. And that's what makes measurement error in X so serious. So why OLS can't fix this? Keep in mind, OLS has no way of knowing. OLS has no way of knowing. It's just a model that you have built. It's not AI, okay? That X has measurement error. And it treats the observed values as if they were exact. It cannot distinguish true variation in X, the real signal, and measurement error in X, which is the random noise. So it interprets both as if they were genuine variation in the regressor. So the result is that the true signal now gets diluted by the noise, and OLS is a weaker relationship than it actually exists. Now, what does this mean for measurement error in X dilutes the true signal? What that means is that instead of seeing the real relationship between X star and Y, OLS is seeing the relationship as being noisy. And the noisier the X, the more diluted, like the weaker that signal becomes, and the weaker this signal is, the flatter the estimated line, okay? So consequence is flatter lines, fitted lines, okay? So the estimated slope is actually pulled towards 0, okay? Not randomly, but systematically, every time in every sample. Now, this systematic pull towards 0 is what we call, so this is systematic. And this systematic pull towards 0 is what we call attenuation bias. Okay? We're having the formal name and derivation for the next video, but hold this picture. So measurement error in X always shrinks the estimated effect. In the next video, we'll prove mathematically that the bias is pulling towards a 0 under classical measurement error, okay? But when it's in the X variable, we'll derive the exact formula and see the degree of attenuation depends on how noisy the measurement is relative to the true variation in X. Because remember, we said that it dilutes the signal, and the weaker the signal, the flatter that line was. So we're going to have a way to measure that flatness in a sense. I hope this was helpful, and stay tuned for the next video.